So at the third annual International Space Station Research and Development Conference, 4 awards were given out for the most compelling International Space Station science projects of 2013. Here to tell us more is the Chief Program Scientist for NASA's International Space Station Program, Julie Robinson. Now the first one I want to talk about went to Carl Carruthers of NanoRacks LLC for his work and NanoRacks work on protein crystal growth. Start off, protein crystals, huge experiment for microgravity research on the station. First off, give us a little more background about why those are such a big deal.
So people are interested in growing crystals on the space station because those crystals, without having sedimentation and convection flow moving through the system, they crystallize more slowly, and there's time for all the molecules to line up and get a more perfectly structured crystal. Now, of course, that depends on if you get the conditions right. And that's what is so innovative about Carruthers' work with NanoRacks. So what NanoRacks did, they are a commercial company. They are using or facilitating researchers to use the ISS, hundreds of researchers they worked with. And what they did is they worked with Carruthers to develop something we sometimes call a crystal hotel. It's an on-the-ground piece of software that they adapted for use in spaceflight in this NanoRacks system. So it was very low cost. And the thing that's great about it is it supports thousands of different experiment conditions all at the same time. So instead of trying to get it perfectly right on Earth, you can screen with a lot of different conditions and run thousands of samples and get a good quality crystal. And what Carruthers showed is from the very first flight of this new crystal system that he got good research results.
Okay, and what are some of the benefits that some of the experiments taking advantage of this new system could potentially lead to?
So there are thousands of proteins in the world where we've identified that that protein is important in a disease of some sort, but we don't know what the protein looks like structurally. If you know the shape of the protein, you might be able to design a drug to interfere with it or assist it or do something else. If you know that protein matters, you've got to have the shape or that structure. And so in getting a good crystal, then you can use either X-ray crystallography or other kinds of neutron techniques to get the structure of the protein. There's a Center for Biomolecular Structure at the National Institutes of Health that has a list of all the desirable proteins that we don't have structures for yet. And then also pharmaceutical companies, many of whom are working on different drug development pathways, will have certain molecules that they want to understand. And so this NanoRacks innovation provides the opportunity for companies like that to very quickly try something on the space station and see if that would be an opportunity for them to make an advance.
Was there any other aspect of NanoRacks' new initiative that led you guys to give them this award?
You know, what we were excited about was just the cost effectiveness and the number of samples that you could get, and the fact that they proved that a number of those crystals really were of very good quality. So it's an encouraging technological improvement. There are other protein crystal growth studies flying this year that will also help us to finally answer that question, can you really get better proteins in space? And so we'll be looking at that pretty comprehensively.
And then let's move on to our next one, and this award went to Nabarun Chakraborty with the U.S. Army Center for Environmental Health Research, and his award was for research being done into how microgravity affects host immune systems. Now first off, again, give me a little bit more background on this project and what led you guys to give this award and why it was so compelling.
Yeah, so Dr. Chakraborty's research over the years has used spaceflight several times, and it's really been focused on understanding the processes of wound healing at the cellular level. You know, when you have a cut in your skin, those epidermal cells, there are stem cells there that have to make new skin to cover it back over, and that's what wound healing is. And you know, it's a very important process. We kind of take it for granted. You know, you cut yourself and you put a Band-Aid on it and then it's magically better in a couple weeks. I learned recently in a personal level why not to take that for granted, because I have a family member that has diabetes, and one of the things that happens in diabetics sometimes is they get poor circulation in their feet and then wounds don't heal. And so she got a cut on her foot that couldn't heal, and she had to get special medical attention and all of those things. So in understanding what are the factors that turn on these stem cells that lead to that interaction, how's the immune system part of that, right? Because the immune system is going there, sending white blood cells to make sure the infection doesn't occur. How does that whole system in the body work? And that was the subject of Dr. Chakraborty's research.
Okay, and I know that there are some challenges to doing similar research here down on the Earth in the presence of gravity. Why is the work being done in orbit in microgravity on the station of particular importance?
Yeah, so it's interesting that microgravity might be a good model for wound healing. What's been found so far is that wound healing seems to be slowed in microgravity, and so you can use that to then see if you can pump up the process, speed it up. Even in a cell culture, if you know what you would expect that culture to do on Earth and you can make it perform wound healing like functions more quickly in space, that's a good model.
Okay, and what's some of the work that might be coming out in the future as a result of Dr. Chakraborty's research experiment?
Well, there is future research that we're expecting that is using more complex model organisms to understand wound healing better. We also expect to see more cell biology studies in the future.
Now we're going to move on to another research study that was looking at the human body and how it works in space. And it was worked on integrated cardiovascular. So again, real quick, give us a quick background on what integrated cardiovascular, or ICV, is.
That pretty large team did almost 3 years of research on the International Space Station looking at the function of the human heart. We know that just based on the fitness levels of astronauts, we knew their hearts were changing when they went into space, but this was the first time we'd really looked at both the physical shape and structure of the heart as well as at its performance. The other thing we knew before this study began is we knew there had been a couple observations of kind of scary arrhythmias. And so we were concerned that if that was normal, if that was something that happened to a lot of astronauts, that could be a significant risk for spaceflight or a significant risk for spacewalks as well. And we didn't have the kinds of arrhythmias. We needed pretty sophisticated Holter monitors to get those measurements. So all of that was wrapped up together in a study called Integrated Cardiovascular. Now you see why it's integrated. And it took about, there were 13 subjects on the ISS. That took over 2 years to get all of those subjects accumulated together, and the results are just starting now to come out, and they were really exciting. And so that's why this team was selected for the award.
Okay, and what are some of those exciting results we're seeing? I know we've learned a lot more about the mechanism of the heart atrophying or kind of weakening in microgravity. What are some of the results that we found?
Yeah, so one of the things that the investigators saw is, of course, the heart got smaller because it wasn't working very hard. You know, on Earth, your heart really has to work to pump that blood out of your legs and keep it up in your head where your brain gets it. In space, everything's floating around kind of equally, and so that's not such a problem. And so that wasn't a surprising result. I was a little more surprised to hear that the heart becomes more spherically shaped as it shrinks. So this, and even the investigators even showed a picture of the Grinch in their charts, because it kind of helps capture that it's smaller, more round, as what the structural changes are. But they also found when the crew members returned to Earth, it responded very rapidly at rebuilding that mass when it was necessary. So this is healthy. When you think about it, a muscle that's not used gets smaller, atrophies a little bit. When you start using that muscle again, you get back in shape and it grows again. And so that really was quite comforting, that when a crew member, say, gets done with a Mars transit, their heart may have shrunk a little bit, but when they start doing more rigorous spacewalks out on the Mars surface in a 300-pound pack, their heart's going to respond to that. Just give them a few days to train into it. Don't make them do it all the first day, and their heart will recover as a good muscle. The other thing that was really important from this study was the data on arrhythmias. And what they found was that if crew members tended to skip a beat here or there on Earth, they tended to skip a beat here or there in space.
So there wasn't a huge difference.
But there wasn't a difference. And so that makes us really comfortable, because that lets us know that whatever we're seeing in the regular health monitoring of crew members on Earth is what it's going to be. The thing that surprised me most in the charts that were presented were some examples of the benefits back here on Earth, because this was a study that was selected completely for exploration purposes. But the data that they got they applied then to a set of patients who have a really rare abnormality. These are patients who have been star athletes, really significant athletes. They showed examples of ballet dancers, marathon runners, people who have been trained up to a really high level of fitness. And occasionally, when those people retire from their sport, their heart atrophies significantly, gets really, really small, and they become almost debilitated, unable to walk, sit up. He gave an example of a ballet dancer who, after she stopped dancing, was bound to a wheelchair, couldn't even sit up without passing out and getting really dizzy and things like that, because her heart, it's like it overcompensated on shrinking down or something like that, on not having those rigorous activities. It's incredibly rare, but he said, there are numerous patients around the country that are suffering from that. And what they were able to do was use the model that they built for the astronauts' heart recovery, and realized that the exercise techniques that we're using to help astronauts recover and grow their heart volume back up might work for these patients, and they had great success.
All right, well, let's move on to our last one, our fourth compelling science result, and this went to Matthew Lynch of Procter & Gamble. And this, my personal favorite, as always, colloids, advanced colloids experiment, which has a huge, huge impact on consumer products.
Right.
Now, first off, what are colloids, and how do they have such a huge impact in everyday household products?
Yeah, so colloids sound high tech, but what they really are is any kind of a solid mixed in a liquid matrix. And so we use them constantly. Detergents, paints, fabric softener, liquid medicines are often a colloid, where you've got some kind of maybe a gel substance mixed in a liquid matrix. And so they're all over in our lives. In fact, Procter & Gamble, which is the company that has partnered with NASA in this particular research, they have estimated that 5 million people touch their products every day, 5 billion people. So almost half the world touch their products in some way every day, some kind of product. Now, I'm trying to get my head around that, because that seems like a big number, but that's what their marketing estimates are. And when you think about how ubiquitous all the different products, how many people wash clothes in the world every day, and how many people do those different kinds of things. So it's possible. And so what Dr. Lynch, who's a research scientist with Procter & Gamble, has been doing for a number of years on the space station is using the space as a model for colloid separation. And the reason he can study things there and not on the ground is because the colloids don't separate out. And so you can get really simple mathematics that you can't do on the ground. Once you understand that mathematics, you can put things back on the ground and model better ways to keep those colloids mixed. And it's nice to have your, say, your fabric softener not separate, so that when you put it in your clothes, you get the right amount. But it could be critical, even though this isn't a Procter & Gamble product, the application to something like a cough medicine, where getting the wrong dose could really be harmful, is important. And so it's exciting to see that work, this fundamental physical measurements of things, modeling of things, actually have these applications in our daily lives.
And just real quick, just some of the knowledge that we've gained from this, and is it already being implemented? You say we're finding these things out on such a small level. What besides just shelf life will this have an impact on?
So Dr. Lynch reported it has already affected the formulation of a number of different products, the work that they've done on the space station to date, and that he's anticipating some of his new results will be in consumer products in the very near future.
So Julie, aside from these 4 compelling research awards that got handed out at the R&D conference, Sam Ting, who does all the work with the alpha magnetic spectrometer, gave a presentation, and you found that particularly compelling also. Why don't you tell us a little bit about what happened?
Whenever a Nobel Prize winner comes and presents at a conference, it's
usually pretty,
by definition a big deal.
Yeah.
And of course, Dr. Ting has been doing research on the space station since 2011 on the alpha magnetic spectrometer. It's essentially a giant magnet and particle detector, and it's measuring galactic cosmic rays. Those are radioactive particles, essentially, that have come all the way back from the Big Bang, and they arrive and they're registered on this detector. He can measure the energy, the mass of the particle, and the direction it's coming from. So far, they've collected over 50 billion observations of galactic cosmic rays, each one of them a data point with that information. And what that's allowing is more and more data to accumulate on the rare particles. So what he presented last week in Chicago was the first data he's ever shared in the higher energy range than has ever been measured by any other instruments. In the past, he had presented data up to 300 giga-electron volts. And last week, he showed us data points up to 500 giga-electron volts.
And so what's the significance when we start getting into these higher energy levels?
So these higher energy levels are less common. And so it takes longer to know how accurate that estimate of its energy would be and so forth. The other thing about them is those are the kinds of particles that you would expect if dark matter is interacting with itself and annihilating itself. So if you have 2 units of dark matter and they interact, they'll annihilate each other and produce a positron. And positrons are the particle that Dr. Ting was reporting on last week. So if you see a lot of high energy positrons, if you see too many of them, then that might indicate a normal kind of source, like a pulsar or something like that. And if you see a medium amount, that would suggest dark matter annihilation. And if you see very, very few, then that would say our theory about dark matter is completely bogus. And so the data point that he showed last week was actually in between those 2 cases with a pretty big error bar. So it was almost a teaser rather, it's not a result you just run to publish, because it shows that he really needs to collect some additional data. But what's so exciting is to see that energy, 500 giga-electron volts, never observed by humankind before. And that was the first presentation of it.
So 50 billion readings wasn't enough. How many more is he expecting?
He probably needs 20 billion more at least.
Big numbers, but exciting stuff.
Very exciting stuff.